Hello students, in this video we will discuss about the solution of two-dimensional Laplace equation. General Laplace equation in two dimensions given by del to u upon del x square plus del to u upon del y square equals to 0, where x and y are independent variable, whereas u is dependent variable. So again we will solve this Laplace equation using separation of variable method, which we have already studied in previous lectures. So this time we have a problem. We have to solve del 2u upon del x square plus del 2u upon del y square equals to 0 under the given conditions, which are: first is u at x is equals to 0 and y u 0 y is 0. Similarly u l y is 0. Here x is l. These are boundary conditions. And in second boundary condition we have constant value of y and x value of x is variable. So ux 0 at y is equals to 0, it will be 0, and at y is equals to a, ux a is equals to sin pi x by l. So we have to find the solution of equation 1 under these conditions. So using separation of variable method, we assume its solution uxy will be x into y type. We will differentiate it partially 2 times with respect to x and y, and putting the value of derivatives in given equation, we get this equation, which is 1 upon x d2x upon dx square is equals to minus 1 upon y d2y upon dy square is equals to lambda. So using first and third fraction we can obtain the value of x, and using second and third fraction we can obtain the value of y. And here lambda is a constant which can take any value, 0, positive and negative. Here we assume lambda is negative, because if we take here lambda positive or 0, under these condition the u is always trivial solution. That's why we go for lambda is equals to minus k square type value. So putting lambda is equals to minus k square here in d2x upon dx square minus lambda is equals to 0 and 1 upon y d2y upon dy square plus lambda equals to 0. When we integrate it, we get x is equals to a cos kx plus b sin kx. Similarly, when we integrate another equation, we can get the value of y, which is y is equals to c exponential ky plus d exponential minus ky. These both are ordinary differential equation with constant coefficient. So u xy, which is solution of given equation, can be written as a cos kx plus b sin kx into c exponential ky plus d exponential minus ky. Now we have to find the value of these arbitrary constant a, b, c and d using given boundary conditions. So first we take boundary condition u 0 y is equals to 0. Putting the value of x is equals to 0 in equation number 2, we get left hand part becomes 0, and in right hand part cos at 0 become 1. So here we have a, sin 0 is 0, and this is independent of x. That's why it is non-zero value. So from here we get a is equals to 0. Now we choose another boundary condition. When x is equals to l, u ly is equals to 0, it's given. And same time, if we use a is equals to 0, equation 2 becomes 0 equals to b sin kl into c exponential ky plus d exponential minus ky. Here this term is non-zero. Also b, which is arbitrary constant, is also non-zero. That's why sin kl is always be 0. So kl should be equals to n pi. That's why we get k is equals to n pi by l, where n is some natural number. Now we'll put the value of a and k in equation 2. After that, equation 2 becomes uxy is equals to summation n vary from 1 to infinity bn sin n pi x upon r into cn exponential n pi y upon r plus dn exponential minus n pi y upon l. So this is equation number 3. Now in this equation we apply another boundary condition, which is u x 0, means at y is equals to 0, u x 0 is 0. It's given here in equation 3. Putting y is equals to 0, we get 0 is equals to summation n vary from 1 to n bn sin n pi x upon r into cn plus dn. So from here we get cn is equals to minus dn. So in equation number 3, replace dn with minus cn, we get this equation. From here, taking cn outside, cn into bn become some another arbitrary constant, say that is rn. So it becomes uxy is equals to cn into bn becomes rn sin n pi x upon l, and here exponential n pi y upon l minus exponential minus n pi y upon l, it becomes sin hyperbolic n pi y upon l, 2 sin hyperbolic n pi y upon l. So here we get 2rn sin n pi x upon l into sin hyperbolic n pi y upon l. Now we use the last boundary condition, which is u at x a at y is equals to a, ux is equals to sin pi x by l. So it gives us sin pi x by l is equals to 2 summation n vary from 1 to infinity rn sin n pi x by l into sin hyperbolic. Here we put y is equals to a, we get sin hyperbolic n pi a upon l. Now we expand this summation sign, we get infinite number of terms having sin pi x upon l, sin hyperbolic pi a upon l. In second term we have r2 sin 2 pi x upon l, sin hyperbolic 2 pi a upon l, and so on. When we compare both sides, the coefficient of sin pi x upon l in left hand part is 1 and in right hand part it's 2r1 sin hyperbolic pi a upon l. In left hand part, coefficient of sin 2 pi x upon l is 0 and in right hand part it's r2 sin hyperbolic 2 pi a upon l. As sin hyperbolic 2 pi a upon l is non-zero, that's why r2 must be 0. Similarly r3, r4 so on will be 0. Only r1 will have some non-zero value, which is 2r1 sin hyperbolic pi upon a pi a upon l is equals to 1. From here we can obtain the value of r1, which is 1 upon 2 sin hyperbolic pi a upon l. Putting this value in this equation 4, putting the value of r1 in 4, we get uxy is equals to sin pi x upon l sin hyperbolic pi y upon l upon sin hyperbolic pi a upon l. That's solution of given problem. Similarly, we will solve one more problem, which is again a Laplace equation del 2u upon del square plus del 2u upon del y is equals to 0. Find its solution under the condition within the rectangle x lie between 0 and a, y lie between 0 and b. Under the condition uxb is equals to 0, means at y is equals to b, uxb is equals to 0, at x is equals to 0 and at x is equals to a, u0y and uay both are also 0. And one more boundary condition, which is at y is equals to 0, x0 is equals to x a minus x. So we will use these conditions to find solution of this equation. So let's take uxy is equals to x into y will be its solution. Similarly, using the process we opted in previous example, taking u is equals to x into y, we can get the same solution for the second problem. For this problem we can find this solution as in previous example we solved. So here we apply these boundary condition. First we apply u at x is equals to 0, u0, y is equals to 0. Applying this condition we get a is equals to 0. After that we apply at x is equals to a, uay equals to 0. When we apply this and simultaneously taking a is equals to 0, from here this equation, from the equation number 2 we get b sin ka c exponential ky plus d exponential minus ky equals to 0. It means ka sin ka is equals to 0, which gives k is equals to n pi, implies k is equals to n pi by a. Using these two value of k and a, 2 becomes in this way. Uxy is equals to n vary from 1 to infinity bn sin n pi x by a into cn exponential n pi y by a dn exponential minus n pi y by a. Now here we apply one more condition. Ux0 is equals to 0. Uxb is equals to 0. This condition will apply. Uxb is equals to 0. After applying this condition, equation 3 becomes 0 equals to summation bn sin n pi x by a cn exponential n pi b by a. Here we put the value of y, which is b, plus dn exponential minus n pi b by a. From here we get a relation between cn and dn. Cn is equal cn exponential n pi b by a is equals to minus dn exponential minus n pi b by a. Or from here we can get the value of dn, which is equals to minus cn exponential n pi by b upon a upon exponential minus n pi b by a. When we solve it, we get dn is equals to minus cn exponential 2n pi by b 2n pi b by a. Putting this value of dn in 3, we get uxy is equals to this. And now taking here cn outside, it becomes cn into bn rn, and in from here taking exponential n pi b by a outside, we have rn exponential n pi by b n pi b by a sin n pi x by a into exponential n pi, as here no terms of exponential n pi b by a. So when we take the n pi b by a outside, here we have to multiply a term exponential minus n pi b by a. So it becomes exponential n pi y minus b by a. And here remaining term is exponential minus, taking minus outside, we get n pi y minus b by upon a. So this becomes sine hyperbolic n pi y minus b by a upon 2, or 2 sine hyperbolic n pi y minus b by a. Now here in this equation 4, we will use the last boundary condition, which is ux0 at y is equals to 0, ux0 is equals to x a minus x. So using this condition, equation 4 becomes x is equals to a minus x is equals to summation 2 exponential n pi b by a rn sin n pi x by a sin hyperbolic minus n pi b by a. From here it becomes minus sin hyperbolic n pi b by a. So here we take minus 2 outside. Now this equation represent Fourier half-range Fourier sine series of the function x into a minus x. So applying the formula, we can obtain the value of minus 2 exponential n pi b by a sine hyperbolic n pi b upon a rn. This is what the coefficient of sine n pi x by a. So we can obtain the value of this coefficient using this formula, which is 2 by a 0 to a function of x sin n pi x upon a dx. Function of x is what? X into a minus x. Now to find the value of this integration, we apply by parts rule and obtain the value of this integration, which is equals to 8a square n cube pi cube when n is odd, and when n is even, it becomes 0. So from this equation we can obtain the value of Cn, which is given by this. Now we will put the value of Cn in equation number 4. Here we will put the value of Rn. Sorry, this is Rn, not Cn. So putting this value of Rn in equation number 4, we get 4n, equation 4 in this form. Hence this is the final solution of given problem. So that's all about how to solve Laplace equation. Thank you.